Space exploration is the most difficult engineering challenge in human history. It requires millions of lines of code, exotic materials, and thousands of brilliant minds working in perfect synchronization. Usually, when a mission fails, it is due to a complex, catastrophic explosion or a hidden material defect that no one could have predicted. But on September 23, 1999, NASA suffered one of the most embarrassing and costly disasters in its history. A state-of-the-art robotic explorer, the Mars Climate Orbiter, vanished. It didn't explode on the launch pad. It didn't get hit by an asteroid. It was destroyed because of a mistake that most high school physics students know how to avoid. Two teams of engineers, one in Colorado, one in California, were speaking different languages. One team was using the Imperial system. The other was using the metric system. And because of a failure to convert a simple number, $125 million of taxpayer money and years of scientific work were incinerated in the Martian atmosphere. This is the forensic analysis of the Mars Climate Orbiter and the simple math error that grounded a space program. To understand why this happened, we have to look at the culture of NASA in the late 1990s. The agency was operating under a new philosophy called better, faster, cheaper. The goal was to launch more missions with smaller budgets and shorter timelines. The Mars Climate Orbiter was the poster child for this era. It was a lean, focused machine designed to be the very first interplanetary weather satellite. Its mission was critical. It would orbit Mars for a full Martian year, 687 days, monitoring the atmosphere, looking for water vapor, and acting as a communications relay for the Mars Polar Lander, which was scheduled to arrive later. The spacecraft was built by Lockheed Martin Astronautics in Denver, Colorado. The mission was managed by NASA's Jet Propulsion Laboratory, JPL, in Pasadena, California. This geographic split is common in aerospace, but it requires rigorous communication protocols. Every file, every number, and every unit of measurement must be perfectly defined in a document called the Interface Control Document. The spacecraft launched on December 11, 1998, aboard a Delta II rocket. For 9.5 months, it cruised silently through the vacuum of space. It performed perfectly. The solar arrays deployed, the star trackers locked on, and the radio phoned home. But hidden deep within the ground software, a time bomb was ticking. The failure centered on a specific file known as the Small Forces data file. Even in the vacuum of space, a spacecraft is acted upon by tiny external forces, solar wind pressure, slight asymmetries in the craft, and the momentum of reaction wheels. To keep the spacecraft pointed correctly, the onboard thrusters have to fire very short, gentle bursts. This is called angular momentum desaturation, or AMD. These firings are tiny, but they change the velocity of a spacecraft. The ground computers need to know exactly how much force was used, so they can calculate the spacecraft's exact position. Here is where the chain broke. The team at Lockheed Martin wrote the software that calculated these thruster firings. Following standard English engineering practice, their software calculated the impulse in pound-force seconds lbfs. However, the team at NASA JPL, which navigated the spacecraft, used software that adhered to the International Scientific Standard. Their computers assumed the incoming data was in Newton seconds ns. This is not a small difference. 1 pound force is equal to 4.45 newtons. Every time the thrusters fired during the 9-month cruise, the Lockheed software sent a number, let's say 1. The NASA software received 1, but interpreted it as 1 newton, when it was actually 4.45 newtons. This meant the NASA computers believed the thrusters were firing with less than 1/4 of their actual power. The tragedy of the Mars Climate Orbiter is that the error was actually noticed, but it was not understood. As the spacecraft got closer to Mars, the navigation team at JPL started seeing something strange. To navigate a spacecraft, they use a method called Doppler tracking. They measure the shift in the radio signal to determine how fast the craft is moving away from Earth. The Doppler data was telling them that the spacecraft was drifting off course. It was moving differently than their models predicted. The navigation team saw these discrepancies weeks before arrival. They were small at first, but they grew larger. The team performed manual calculations and realized that there was a force pushing the spacecraft that they couldn't account for. They even filed an official ISA, an Incident Surprise Anomaly Report. But here is where the better, faster, cheaper culture may have played a role. The team was overworked. Communication between the navigation team and the spacecraft operations team was strained. The anomaly was dismissed as a modeling error or an issue with the solar radiation pressure model. No one suspected that the fundamental units of math were wrong. They trusted the computer code more than they trusted the raw observation. On September 23, 1999, the moment of truth arrived. Mars orbit insertion. To get captured by Mars gravity, the orbiter had to fire its main engine to slow down. It needed to skim the top of the atmosphere to use aerobraking. The target altitude was 226 kilometers. The absolute minimum safe altitude was 80 kilometers. Any lower, and the friction from the atmosphere would tear the solar panels off and burn up the probe. Because of the unit conversion error, the spacecraft was actually 170 kilometers lower than the computer thought it was. At 9 a.m. Pacific time, the main engine fired. The spacecraft went behind Mars, cutting off radio contact with Earth. This blackout was expected to last 20 minutes. The team in the control room waited. 20 minutes passed. Silence. 25 minutes passed. Silence. 30 minutes passed. The flight director paced the room. They sent commands into the dark, hoping the spacecraft had just gone into safe mode. But there was no answer. Later analysis revealed the heartbreaking truth. The Mars Climate Orbiter had entered the atmosphere at an altitude of just 57 kilometers. It was traveling at huge hypersonic speeds. At that height, the Martian atmosphere is dense. The spacecraft would have begun to tumble immediately. The heat shields were not designed for that pressure. Within seconds, the aluminum structure melted, and the $125 million robot disintegrated into a streak of fire across the Martian sky. The subsequent investigation was brutal. The Mishap Investigation Board didn't just blame the math, they blamed the process. They found that while the root cause was the failure to convert pounds to newtons, the actual cause was a failure of systems engineering. Lack of verification. No one had ever actually tested the file transfer between the Lockheed software and the NASA software to ensure the units matched. Ignored warnings. The navigation team's concerns about the trajectory drift were not elevated high enough to stop the mission. Complacency. The team assumed the software was correct because it had been used on previous missions, like Mars Global Surveyor, not realizing the code had been updated. The loss of the Climate Orbiter was a turning point for NASA. It effectively ended the extreme better, faster, cheaper era. It forced a return to rigorous, redundant verification. Today, NASA strictly enforces the use of metric units for all mission-critical communications to prevent this exact scenario from ever happening again. The Mars Climate Orbiter is a reminder that in engineering, there are no small details. A unit of measurement is not just a preference. It is a definition of reality. When we ignore the boring, basic checks in favor of the big, exciting launch, we court disaster. The cost was $125 million and years of lost science. But the lesson, always verify your inputs, is priceless. If you enjoyed this deep dive into system failure, please hit the like button. It really helps the channel grow. And if you want to see our next analysis on a massive infrastructure collapse, make sure you are subscribed with notifications on. I'm Build and Rise Network, and I'll see you in the next analysis.